humanitarnych масштабов. And you see the new Nobel laureates on the screen above us. Here are some brief biodata. Shukuro Manabe was born in 1931 in Shingu in Japan. He got his PhD from the University of Tokyo, and he is, since many years, senior meteorologist at Princeton University in the United States. Klaus Hasselmann was born in Hamburg in Germany, also in 1931. He got his PhD from the Georg August Universität in Göttingen, and he's now at the Max Planck Institute for Meteorology in Hamburg. Giorgio Parisi was born in 1948 in Rome, in Italy. He got his PhD at La Sapienza Università di Roma in 1970, and he remains at La Sapienza as professor. With that, I'd like to ask Tors Hans Hansson to make some remarks on behalf of the Nobel Committee. Hans, please.
Thank you. So, many of you might believe that physics is only about simple and ordered phenomena, like the Earth in its perfectly elliptical orbit around the sun, or atoms that are in perfect crystal structures, or electric currents that flow predictably from the socket through the lamps or to your refrigerator. But physics is much more than this. One of the basic tasks of physics is to use basic theories of matter to explain complex phenomena and processes. Like how materials like glass are structured, or what is the development of the Earth's climate. These studies require deep intuition for what structures and what progressions are essential, and also mathematical ingenuity in order to develop the models and the theory that describes them. Things at which this year's laureates are true masters.
Thank you, Hans. John Wettlaufer, please tell us more about the science behind the prize. The floor is yours.
Thank you. From a distance, complex physical objects can appear simple. From atoms to planets, taking a closer look always reveals structure. We are awash in complexity at every scale that we observe. As scientists, we ask, how much detail is required to explain the observations? Must we track every water molecule to explain the ocean? What length scales are important to understand if we are going to see what phenomenon emerge from such a system? One half of this year's prize focuses on the physics of Earth's climate. That's an old topic in physical sciences. It began in 1824 with Fourier. Fourier recognized that the atmosphere of Earth is ostensibly transparent to the visible radiation from the sun. And yet the Earth converts that visible radiation into what he called dark heat, the dark energy of Fourier's time. He surmised that this must interact somehow with the atmosphere to keep Earth warm. Scientists subsequently measured in the laboratory the absorption and emission of what we now call infrared radiation, Fourier's dark heat. And it was to take 70 years before Svante Arrhenius took these observations and these measurements and combined them in the first mathematical model of climate. And he predicted that if the concentration of greenhouse gases in the atmosphere increased, so too would the temperature of the Earth. Another 70 years, 2 world wars, and the computer revolution would pass before Shukuro Manabe and his colleagues knit together this web of processes, including key aspects of the atmosphere's thermodynamics and dynamics, and made the first prediction, reliable prediction, that if you double the carbon dioxide in Earth's atmosphere, the Earth's surface temperature would increase by 2 degrees Celsius. And about the same time, Edward Lorenz taught us about chaos, that the weather is chaotic. It evolves rapidly and becomes unpredictable after about a week. Could it be that Lorenz's chaos was noise to the climate? So thought Klaus Hasselmann. He made the analogy between the rapidly varying weather and the slowly varying climate and Brownian motion from Einstein's theory, whereby rapid collisions of water molecules with pollen grains displace them slowly over time. He then predicted that the weather on timescales of days influences the ocean on the timescale of years. He went further with these ideas, and he constructed a systematic statistical way to compare measurements, observations, and models to extract the fingerprints of particular physical processes in the climate system. Galileo peered into outer space with his telescope. Giorgio Parisi peered into inner space with mathematics and asked questions about apparently banal materials like glass that were deep and impacted many areas of physics. We're used to taking a liquid like water and cooling it under normal circumstances. It freezes into a periodic, well-ordered structure. However, if we freeze the liquid very rapidly, it becomes another body. We call it amorphous. It has attributes of both solid and liquid. We can understand the difference between these systems in daily life because we see them in glasses all the time. Glasses fracture like a solid and yet flow like a liquid. We can consider their energies, their energy landscapes. The periodic solid has a simple landscape. A particle in a bowl can only find one place to rest. In a glass, the landscape is complex and rugged. It's not clear where particles will reside. They are frustrated. Giorgio Parisi studied a magnetic version of a glass called a spin glass. Imagine that we can decorate this triangle with magnets that can either have their north poles up, north poles down, or they can flip between north up and north down. Okay. However, we have the stricture that no two corners can have the same orientation. So when we place the third, it breaks the stricture, it breaks the rule. So another one must flip which drives the flipping of another one, and so forth, forever. The system is perpetually frustrated. Giorgio Parisi tamed this frustration, this complicated landscape, by building a deep physical and mathematical model which was so broad that it has impacted a vast range of fields far beyond spin glasses. From how granular materials pack, to neuroscience, to how we compute, to random lasers, and to emergent phenomenon far beyond what he envisioned in the 70s when he started this work.
Thank you very much, John. And it's now time for questions from you, ladies and gentlemen, in the audience. We hope to have one of our Nobel laureates with us, but I don't know if he is on yet. He is. Okay, very good. Professor Parisi, are you there?